Today I hope we can put together everything that we went over on Monday and Tuesday's lectures. And in particular, I'll just spend a little bit of time on the slides for our these 2 hours of the presentation, and then I'll dedicate most of the time to going through the code, which I have available on GitHub with full working models. So we've seen kind of the snippets of the code and how to put things together, but I really want to show how that looks in a complete form so that you can go and create your own models. The links will be sent out later today. We were going to send them out earlier, but we thought we'll send them out with a feedback form and some closing remarks after today's workshop. The website, though, if you navigate to math.purdue.edu, then ~n_Winovich/workshop.html is where our videos will be posted. They'll also be on YouTube. It may be easier to find here. And then that has a link to the GitHub repository containing the examples and, in particular, the full working models that I'll be going over today. Okay. So as I mentioned, I want to start off with a brief overview of two different types of models, a classifier and a generative model. And really, these are just two basic examples which you can build upon, but they're characteristic of two kind of fundamental ideas in machine learning, namely that of going from structured data to specific labels or properties, and then conversely, going from certain properties or from noise and creating structured data. So that's what we'll start talking about in this first half of today's talk. So for classification, what we're aiming to do, as this picture suggests, is take a piece of input data which has some structure, some high-level features, such as curves in this case, or symmetry, and we want to identify, classify, or label what that data is, what that represents. So in this case, and kind of a typical example is the MNIST database of handwritten digits available on Jan LeCun's web page listed here. So in this example, there's a collection of handwritten digits which are stored in black and white format as pictured here. And a kind of basic first task we may ask is, how can we assign labels distinguishing what number is represented by a given image. Okay, so we have a picture of a 2 here, and we want to assign the label 2. So if we approach this naively, we may actually be able to define some defining characteristics of the images. Conventionally, things like symmetry or pixel intensity could be used. And so we could notice that maybe an 8 has more symmetry than something like a 3. And this could be used with some classical machine learning techniques to accurately classify most of the digits. The problem with that approach is that it's not very scalable. We can't really just manually assign labels, or rather features, to kind of more complex data sets. Handwritten digits are somewhat simple in that regard. So we want to identify or create a more scalable approach which automates the idea of finding features. And a natural idea of doing this is to use something like a convolutional layer, a series of convolutional layers, which can extract or identify patterns or features which characterize the digits. So we can think of using a sequence of these filters, and we process multiple times this kind of upper left-hand corner patch, and we notice that maybe, for instance, there is a straight edge here. And maybe that gives us a clue as to what this number is. So convolutional layers can be applied. You can also approach this with a dense network, but as we mentioned yesterday, for spatially organized information, a convolutional approach is typically superior. Now, we already know how to construct these convolutional layers. What I want to talk about, though, is the particulars of how we evaluate the loss in this case. So we're trying to assign a label. We have our convolutional network. We make a prediction of some sort. So how do we define the loss function in a way that's suitable for this particular problem? And a convenient way to approach this is through the use of the softmax function. So the softmax function can be used in particular to convert an arbitrary sequence of numbers, in this case labeled z. So we can think of these as the outputs of our neural network, and convert them to some scaled probability values. In particular, they're probability values which sum to 1. So they're interpreted as mutually exclusive. In the case of digits, we know that the answer is only 1 of the admissible labels. In particular, in the last example, it was 2. So we can't have an image which is both 2 and 3. So we'll assign probabilities which sum to 1 and choose the value which is highest as our prediction. So the rescaling is actually quite simple, and it's used in a variety of things from statistics, mathematics, and here in machine learning. We basically convert these arbitrary real numbers to positive values using an exponential function, and then normalize them by summing those values up and dividing these exponential functions. Okay, so these will now sum to 1 by construction. And just a note on terminology, those output values that we had before we rescaled, before we applied the softmax function, are referred to as logits. And these are often produced by our network or stored in our graph and passed to a fused operation. So we typically don't actually apply this manually. We'll pass it for reasons of efficiency and, more importantly, in this case, numerical stability, so that we compute, as we'll see in the next slide here, the entropy, the cross entropy, at the same time that we're computing the softmax function. And the reason why this makes some sense is we're about to take the log. Okay, so we're taking the log of something that we just put inside of an exponent. And so we can see how this clearly has some ways that we can compute this more cleverly and avoid some different rounding errors or underflow or overflow. So the cross entropy is the loss function, or defines the loss function for a typical classification example. So we can imagine we've applied a softmax function, and we have probability values. We have some labels listed in a one-hot encoding of the output. So here we have a sequence y, but only one of them is 1. The rest are 0, as we mentioned in yesterday's talk. And we define the cross entropy as follows. So basically, we scale the log probabilities, the negative log probabilities, by whether or not that particular probability corresponds to the true label. So in reality, there's only going to be one non-zero y value in this case. So it will reduce, in the case that the label is k, to just negative log and then that probability value. Okay, so by construction, and the reason that this makes sense to use in the classification case, this loss function is 0 exactly when our predicted probability is 1. So when we got it exactly correct, then there's no loss. We've done well on that example. So as I mentioned, we actually want to avoid just doing this manually, step by step. In TensorFlow, they have, and they've recently updated the old implementation, a softmax cross entropy with logits version 2. So the with logits means that you're going to pass it those z values, not the softmax outputs. And again, this is for stability purposes. Okay, so that's really all of the theory behind, I mean, not all of it, but a good summary of the theory behind classification. Now I want to go into how we actually put this together. Put together what we've learned, in particular in the first day of the workshop, into a full working model. And so, as I mentioned here in GitHub, I have a repository, TensorFlow examples, and within that, a models folder which contains a classifier, as well as 2 other models that we'll go over today. Now, for all of these models that we'll discuss, there are 4 kind of helper files just used to organize our code. There's a utilities file which we won't need to use, but this is used for writing those TF records files. So if you're interested in kind of going through a step-by-step guide to writing a TF records file, this file on the GitHub repository shows you how to do that, or at least in the case of the MNIST data. The flags file, as we mentioned in Monday's talk, specifies the hyperparameters. So if we take a look, if we go over here to the models folder, I have some brief explanations of how to run things. Hopefully, most of this is just review, and a link to where to get the MNIST data. But if we go to the classifier, or the flags rather, what we see are just a list of basically arguments that I've assigned. So we don't really need to think about these too much, but I want to define all of the different settings for my model so that I can pass it command line flags and change it on the fly without having to go into the model. So I've just added things like where the data is stored, how often to display, the number of training steps I want to run, and the number of training data examples that I have, batch size, etc. So there's just some training parameters, and then I have specific ones for each model. So in addition to those, I have a classifier set of arguments which has things that are specific to the classification setting. So for instance, label count. There are 10 labels corresponding to the 10 digits. So the flags file, as I mentioned, contains the hyperparameters, things for like training, settings for displaying and saving, and the remaining two files are more directly applicable to the model. In particular, we're defining the layers, the actual network layers that we'll be using. And again, these are those what I referred to as custom layers, but really they're just a way of adding default arguments. For instance, if I just call dense, it will refer to tflayers.dense. But it will have a default activation function. In this case, I've just set it to none. And some default weight initializer, which I've used the same for all layers in this case. That may or may not be appropriate. But just for an example case, you see how we can set some of these up ahead of time. And then convolutional layers, I've given it a default stride of 2, for example, and a default kernel size. So we can call these in a little bit more brief function definition, or a brief call. And then lastly, what I referred to as the miscellaneous file defines the parsing function and the early stopping hook. So I won't go through it in detail, but if you are interested in implementing the early stopping hook, you can take a look at the full code for this in this file. And then the parse function is very important because this is how we unpack the TensorFlow TF records file. And in this case, it's relatively easy. So if I go to the parse MNIST data example, which we'll be using, this is going to output a one-hot label and the resized image array. Resized by which I mean it's been reshaped back into a square array of size 28 by 28 by 1. Remember, we had flattened it to put it in the TF records file. And so in this function, which will be called by our data set, we go through and we basically pre-process this. So we're going to decode from bytes, cast it as a float after reshaping it, and then divide it by 255. So these are unsigned integers, 0 to 255, and we'll just rescale them to be values between 0 and 1, just as a normalization measure. And then we'll decode our label, which was already in a one-hot format, and cast that as a float 32. So TensorFlow, by default, works with float 32, and sometimes NumPy assumes float 64, so it's always a good idea just to cast your values as float 32, just in case. So this is what we'll use to extract from our TF records file, and that will be called in our model class. So again, when we're defining these models, I like to kind of organize them as a class, and then just a small main function at the bottom, which is run at the start. So if we scroll down and try to go through this in order of execution to the bottom, what is first called is the kind of small code block at the bottom. And since we're running this from the command line, it will call this, which will direct us to main. We'll get our flags from the flags.py file. We'll initialize our model and unpack those flags using the methods that we learned on Monday's talk. Then we'll get some of the settings that we need to initialize our session, like how many training steps do we want to go through, specify some early stopping settings, and then initialize our monitored training session. So we give it the checkpoint directory where we want to save those models, the stop at step hook, which limits us to, in this case, 20,000 training steps, the early stopping hook, which is defined in the miscellaneous file, and then I set the summaries to none because I'll write my own summaries for training and validation, and set a checkpoint step. Remember, after you do this, you want to pass the session to the model, and then you can begin training. Okay, so at this point, we've gone through a few things in the class, but they're relatively standard. So we've, for one, done the init method. As I mentioned, we unpack those flags that it's been passed. Just to be safe, I check to see if the training records are there, if they already exist. And if not, I'll just call a function in the utils file to write those or to create those. After I know that the files exist, the data set exists on my file system, I can initialize my data sets. And I've just opted for kind of the simple approach, kind of the first example that I showed. And all that you really have to see is this first example. The second for validation and third for early stopping are really just cut, copy, and paste, just with training replaced with validation. So if we take a look at the data set that we've created, so we, again, get the, so we find the data directory, which is specified in our flags, and look for the file, which is named training.tfrecords. We then map our parse function to unpack the training examples. We shuffle and repeat, batch it into our specified batch size, and then fetch some examples just to make sure that we have examples ready to be processed if the network is ready to take more examples effectively. And then we also have to make a one-shot iterator. I don't know if I commented on it in the first day, but there was actually a note at the bottom of one slide that said you didn't have to do that, and I was mistaken. You do have to do that. So we're going to make all of these one-shot iterators, and the feedable iterator will take the dataset handle from the iterator itself. So just a minor thing, you do have to include that line. So now we have a data set. At this point, we have our data set, we have the session assigned to the model, and we've called train. So if I scroll down, we're going to be executing the train portion or method of the code. And this will first show us a list of variables. There's a kind of convenient command, which is, I believe, in the utils file. Let's see here, which shows you all of the variables that your model has. And I can show this, an example of this as well, of what the output looks like. Yes, so this line here, it gives us a kind of easy way to get a readout of all of our network layers and the sizes in particular. If we want to make sure that everything has the size that we think it has, this is a really easy way to do that. And so if I go over here, I have a SSH session open, and I just entered a virtual environment, and I have my model folders here. So I can run the classifier model, and I'm using a GPU, so I'll increase this. Using a GPU, and I'm also using what's referred to as thread caching memory allocation, I believe. So that's the explanation for that first part. It's just a kind of a technical detail you may or may not want to look into. And then we can run this, and what we'll get at the beginning is a readout of our network. Okay, so some errors like that, kill it. And this here is the output of the show all variables function. So we see that we get kind of the shapes, the number of bytes, and the names for our network layers. So it's helpful for just making sure that what you've written is actually being implemented the way that you think that you've implemented it. So that's what happens at the very start of our code. So when we start training, and I'll just display some updates, like we're initializing our variables. And then, as I mentioned, we need to get our handles for our data sets. So I'm going to run self.dataset and get the string handle, and the same for my validation data set. So these will be used in the form of a feed dictionary passed to the model to determine whether it is training or testing. And now we see we have the while not self.sesh should stop corresponding to the monitored training session that we're using. It knows when it has to stop. And we retrieve our global step, which is defined in the init method of the model class. And I have some technical things to avoid issues with the custom hook. Sometimes its request stop is not caught in time. But the important things to look at here are the feed dictionary. So again, we don't want to pass much information using feed dictionaries because there are more efficient ways to go about that. But what we can pass are a Boolean and a string relatively quickly. So there's no problem doing that. So we're going to give it the dataset handle and a Boolean corresponding to whether or not it's training. And then basically, here we have some decisions, whether we're going to make a summary, whether we're going to display the loss to the standard output, and whether or not we're going to, I guess that's it, just in any 4 of those combinations, including just optimizing. So really here we're just doing our optimization step, but every once in a while we'll write a summary for our training process. We can optionally plot some of these predictions, and then it's also useful to save validation summaries. And again, all that we need to change is the dataset handle that we feed. Now we use validation handle, and the training parameter should now be false. But we can do this the same process. So that's the entire train aspect. So what is this running? What are we optimizing? That's defined in the build model component. And we see that we have our dataset handle as a placeholder. So it's set to receive the string handle that we pass it. And we created this feedable iterator and made it or assigned self.data to the getNext method of that feedable iterator. We also define an exponential decay or apply an exponential decay to our learning rate. And we define the training placeholder. And for convenience, I've just created this evaluate model to produce, as I mentioned, the logits is what we're going to use for our model, our predictions. And I've also produced the probabilities just for convenience. Later on, I may want to just add up the misclassifications. So I'm not worried about stability here. It's just I want to know what was the argmax. And then we can count the misclassifications directly from the probabilities. So the evaluate model in this case is relatively simple. We unpack our data. So our data, again, from the parse function, is returning images and labels. So I believe it's open here. It's in miss. If we just look, so where is this coming from? Well, we've decided to return a list of 2 values, the image and the label, in our parse function. And that's exactly what we're unpacking here. The data is coming from that parse function. Now we apply the classifier. We'll get our probabilities and our logits, and we compute the cross entropy only using the logits. okay, as we mentioned. And if we just go up, we can see, so the logits are used. I just called it compute cross-entropy, but really it's a reduction by mean of the softmax cross-entropy with logits version 2. And our classifier network is defined. Again, this is a really, really simple model, but I've just added convolution, followed by convolution, batch norm, leaky ReLU. Then I've reshaped, as is somewhat typical, so that I can convert it to a dense layer, and then finally to a dense layer with a number of nodes corresponding to the label count. So this will, in our case, predict 10 values corresponding to the logits for 0, 1, 2, all the way through 9. And that is, for the most part, all that there is to it. And so we can try, if we run this, so on this computer, should go relatively quickly. So we can see this is running on a computer in the lab I work in. And we have early stopping checks. It just goes out. There's nothing too fancy. You can have more kind of readouts or less readouts just by specifying things in the flags folder. And at the end, we should get an evaluation of how this network performed. OK, so this will go on just for a little bit longer. So I'll go back to the slides for a moment. We'll come back to that. But the nice thing about the setup, there's quite a bit that we've gone through already. But the nice thing is that when we go to something like a generative model or a completely different model, there's only 1 or 2 blocks of the code that we have to change. Okay, we really can use everything all over again. And in reality, you may want to look into using the super method and class inheritance so that you don't actually copy and paste that. You can just inherit from a kind of super class or a model that's larger. In this case, I tried to limit the number of kind of Python abstractions that I've used. But as we'll see here, to create this fundamentally different network, one in particular which is going to go from unstructured, basically noise, and create something, create an image, we can really just take the model we have already and replace the classification method with a generation or a generative model method. Okay, so a generative model, as I mentioned, is now aiming to produce something. We want an image of a 2, for example, or an image of a handwritten digit. And the kind of underlying idea is that we can imagine there's some universal distribution. There's some kind of defining list of all of the possibilities for a correct handwritten digit. And we have a data set which represents samples from that universal distribution. There's just some of the possibilities. And we want to learn from those samples and basically mimic that distribution, that sampling process. So we take, for instance, random Gaussian noise or random uniform noise, and we want to predict something which still looks like a digit. The basic model structure for this is kind of the opposite of what we were using before. So we're going to start with a low-dimensional kind of noise vector, and we'll build that up and hopefully get some type of structure in that. So in most cases, what we'll want to do is use something like a convolution and interpolation procedure so that we're kind of building this up in a spatially aware fashion. You can do it with fully connected, but you're likely to get better results using something along the lines of this type of structure. So we start with a noise vector. We can shape that into a square and then begin a convolution interpolation procedure. The one kind of key difference is that whereas in the classification setting, our task is relatively easy. We have this structured data, and we just want to get one little label, one number out. In the context of generating data, if we want to look at this, I mean, it seems a little bit harder, and we're going to have to help the model out a little bit. We're going to have to be more creative or more clever with how we design this. We're just taking noise, legitimate noise, and we want to somehow produce something which is organized in some high-level way. So the issue in particular is that we need a way to actually quantify how real its predictions are. So say we just kind of start training our network, it makes a prediction. How do we know if it's real or if it's fake? For instance, if our model generates something like this, which was an example from the generative model that I have on GitHub, just after maybe 250 training steps, we see that it's something like a number. I mean, it's not complete noise, but it also has some issues, and it's quite hard to really say what loss I should assign this kind of quote-unquote digit. Okay, so we may have some panel of experts, and this does actually happen in some cases. You can have people, have a group of people assign a value to, say, I think I heard of an example with analyzing pictures of stars and looking for lensing. And you could have kind of a democratic vote on whether or not it has that lensing or not. So that's one way, but it's clearly not scalable in most cases, especially maybe for like graduate research. We really need to be able to do this ourselves, or to automate it so that the computer can do it, instead of depending on a large resource of willing volunteers. So the way that we do this, instead of asking some community of experts or for their subjective opinions, is to introduce a discriminator. And this was actually defined by Goodfellow et al. In 2014. And it's really quite natural in a way, and it's quite clever in that we can actually define a very credible score or rating by training a separate model or separate network component to basically work to distinguish real from fake. And we'll see as the subsection title suggests that this is an adversarial or a type of competition that we create for the two network components. Okay, so the discriminator in particular is going to try to assign a value of 1 to true examples, things from our data set, but we'll also send it things that have been randomly generated from our model, our generative component, and we want that to be assigned a value of 0. So typically these are designed somewhat in the reverse direction as the generative model. Now we want to go from the structured data just to a single label, is it real or fake? Or more kind of generally, we want something like a convolutional approach just to take advantage of spatially structured patterns and details. So the adversarial part of this kind of setup is that we want to actually have the generator competing against the discriminator. So the discriminator, again, is working to learn to distinguish real from fake, but we want our generator to be able to produce things so close to the true data distribution that it's not possible to differentiate. Okay, and so this, again, is a very natural approach. We want our generator to be making realistic images. And how can you quantify what realistic is? Well, one way to kind of quantify that is to say another neural network can't tell the difference between the real and the fake. The things that you're generating are close enough that our model cannot differentiate between the two. And so the way that we train this, or that we actually set this game up, is through the loss function. So the loss function, again, is the only real guidance that we have, and it's what we can use to create or establish this game. So the loss function will be divided into two components, one loss for the generator and one loss for the discriminator. And those losses will be defined so that the minimum, in the case of the generator, corresponds to fooling the discriminator. So the discriminator's value on fake data is equal to 1. Okay, so that's when we want the minimum. The discriminator thinks that the generated data is real, 1 corresponding to real. Okay, so if we can do that, then we are doing a good job in terms of generating images, and we shouldn't penalize the generator. On the other hand, on the other side of this game, we want the discriminator to foil this kind of plot. We don't want it to be fooled. So what we want to do is define a loss function so that the discriminator basically is encouraged to assign the correct labels. So we want the values on generated data to be 0, and the values on true data from our training set to be 1. Okay, and just from this very basic heuristic argument on the previous slide, we can make a very natural selection using negative log probabilities, basically. But here we can just see the functions do exactly what I've described in the previous 2 bullet points. The generative loss takes its minimum. So if we're looking on this graph, when the value of the discriminator on the generated data is equal to 1. The discriminator thinks that it's real. And the discriminator loss has 2 components. One, how does it handle the true data? So this says the true data should also be set to 1. But the fake data, so to speak, or the generated data, should not be set to 1. It should be set to 0. Okay, if it's set to 1, if it's fooled, it gets a high loss component. Okay, so so this definition is just a very basic approach to implementing these 2 bullet points, and these 2 bullet points are really just going after this game, this idea of an adversarial game. Okay, so I think it's quite nice. And also, if you consult the paper, Goodfellow et al., there's a probabilistic logic, a proof in a certain context of why this works. So the distribution, the minimum of this setup, the discriminator and the generator, which minimize the loss, correspond to the case when the generator is in fact sampling from a distribution which is identically distributed with the universal data set. So if you're familiar with probability theory, you can go through that paper, and it is quite nice. This paper, as well as the paper I'll talk about in the second half, are 2 of the few machine learning papers that have, to some extent, I guess, that have rigorous probabilistic proofs. So that's one of the reasons that I've chosen to present them today. And here, I've just listed the algorithm in pseudocode form. Again, very, very simple. The one thing that we'll have to do when we look at our TensorFlow code, so the fundamental difference between the classifier and the generator in terms of coding, is that we're going to have to take derivatives with respect to 2 different sets of parameters. Okay, so we're going to have to make these updates kind of separately, and we'll see how to do that. Okay, so we have a simple example, and let's actually check how our classifier did. Okay, so we see we've finished training here, and on that relatively simple classification model, we've evaluated on training and validation, and our training loss, or rather our training misclassification, was 0. So we're completely fit to the training data, and we've only misclassified about 0.1% of our validation. So this is quite accurate. So it's really kind of a powerful kind of model using just that batch normalization. Already takes care of most of the overfitting, and you can tweak things and add some kind of more clever things to get this down a little bit. But for the most part, we've kind of solved this problem, at least for just the simple handwritten digits. So I just thought I'd point that out. I guess we can look at this on GitHub now. So as I mentioned, almost everything will be the same in the GAN model. To the point that I would say at least 90% of the code is exactly the same. And I've even reused, I'll just point out, for the discriminator, I've actually just cut, copy, and pasted the classifier network. So the classifier seemed to do a good job at figuring out what number it is, so it kind of makes sense that would probably do a good job at figuring out whether it's real or fake as well. So I've taken the exact same classifier, I just refer to it as a discriminator now, because it has the same general structure, right? It takes structured data and it produces like 1 value or 10 values in the case of classification. So I just reused that, and for our generator, I've really just kind of flipped it as those diagrams suggested. They're really kind of mirror images. So I start out with dense layers, use batch normalization, but then I reshape it eventually and use convolution, in this case transpose. You can also try it with interpolation and see if that improves the performance. Okay, so we have our generator and discriminator. The real difference that comes up, as I mentioned now, is going to be our loss function. So in the evaluate model section, again, just following the same structure as the previous class, we're going to apply our generator to get our predictions. And these predictions are what I've been referring to as generated or kind of fake images of digits. And now I want to evaluate my discriminator on those predictions. So this is for our first part of our loss function. If I go over here. So for this component, I've generated some fake data. I want to compute this loss, effectively, the generator loss. So I'll call it discriminator on fake. Those are the probabilities, but we're really going to use the discriminator's fake logits for numerical stability. And we'll compute the cross entropy by supplying the logits, and then and this is just a one-hot encoding, basically. So this is actually, yes, I believe so. And so this is going to compute the binary cross entropy for the model. And the binary cross entropy is exactly this. So yeah, I forgot to mention one thing. This is actually the case of a single. So if we just have one prediction, again, going back to the cross entropy, we had a sum. But once you know what the correct answer is, it's just negative log of the pk value was our notation. And so this is a case of that. So we've implemented that loss in this form just so that it makes use of that optimized and numerically stable calculation with logits, effectively. And so then we do the same thing for calculating the discriminator loss. So now we're going to work with the true and the false. And so we'll do the same calculation. So we're working with the real data for the first term. We evaluate the discriminator on that real data. So this data is coming from our data set. And we compute the cross entropy, again, with ones, because that's real. We want it to be 1. And we compute the second term, the fake values. So this term here, the discriminator's loss on the fake logits, by computing the cross entropy, but the correct answer is 0 in this case. So a little bit technical, but so the cross entropy is basically told we want it to be 0 in this case because they're fake, and we want it to be 1s in this case because they're real. Whereas in the generator loss, even though they're fake, we're trying to fool the generator or the discriminator, so we still want the discriminator to get 1s. Okay, so that's kind of a brief explanation of that. Okay, so now we have the losses, but we also have to compute the gradients according to this algorithm. We need to do something a little bit different. We haven't talked about this before, but the way to do it is relatively straightforward. What I've done is I've assigned names to all of my layers in such a way that the discriminator's variables start with D underscore, and the generator components start with G underscore. So if I just scroll up, this is just for convenience, but I have D underscore dense, D underscore batch norm, all of this, so that we're going to get all of these variables and update selectively based on whether we're training the generator or discriminator. So in particular, we define a discriminator optimizer and a generator optimizer, which will both be called, for some reason, we typically have a larger learning rate on the generator, and this is typically because it's easier to tell if something's fake or real than it is to create something real. So we kind of need to learn more in the generator case. So that just a little note. But the key here is that we're going to be minimizing the discriminator loss, obviously in the discriminator optimization step. And we're only going to use the variables in the list D underscore vars. And likewise for the generator optimization step. So nothing too crazy. Since we use batch norm, we have to use the with control dependencies, get collection, graph keys, update ops, as we mentioned. But other than that, everything is the same. And we get predictions which are still quite accurate. So let me see if I have these. So if we go to the final predictions, we see something like this. Looks like a 5. And so this has been generated from random noise. So that, let's look at all of them so we can see. We'll see that it's not quite perfect, because if you look at the loss, it actually, there's some divergence. So this network could be improved. I used a pretty basic, pretty naive version. But still, we see that these look, for the most part, like digits. And actually, it's quite impressive, because if you actually look at the training examples, some of the digits are quite questionable, the ones labeled real themselves. So we can cut it some slack. But it certainly is making predictions that are quite accurate. So now we can generate as well, which is nice. In addition to this, there are a large number of models. And one source that helped me a lot at the beginning of TensorFlow implementations is at the following GitHub repository. It's very nice. The only thing is that it's a little bit outdated in terms of the TensorFlow implementation, but I've taken basically the model structure, just like the dense convolutional for my GAN model and the VAE from that, and kind of updated it in this code that I've been showing you. But if you want to see other variations, there's, I think, like 12 models on this page. And they have nice diagrams, a nice overview of the different loss functions, references to the papers. And there's a wide array of variants on this generative concept. So one of the kind of more interesting ones, maybe I'll play it over the break, while we take a break here in a few minutes. But a very kind of high-resolution version of what we've just done was implemented at NVIDIA by this progressive growing of GANs. It's a very interesting concept. Basically, they started out with a low resolution, and then they added on, once they got some kind of a good performance, they added on at the beginning and the end additional convolutional layers. Okay, so maybe they started out at like 16 by 16, just these really blocky pictures. It got trained like that, and then they extended it to 32 by 32 and extended it until they got to, I believe, like 1028 by 1028, and they generated, these are fake people. They're not people from the training data set. They don't exist, but they look quite natural. So it's pretty impressive. Yeah, you can see like there's like some artifacts, some examples they don't look like people, but it's kind of a really interesting case, and I'll show it for you later. And then here another kind of interesting example. We obviously probably have better applications for this, but style transfer is something that actually is coming up more, but here's just a kind of the cycle GAN has a really interesting way. It basically goes from the horse to the zebra, and then the zebra back to the horse, and it uses this cycle concept to double check itself, to kind of correct itself and work in a, I believe, unsupervised fashion. But we're starting to use these things now for adding style. When we're training, if you're making a training data set, you can use synthetic data. Maybe you use a computer model or like a graphics, like a video game even. If you have some rendering engine and you can do physics in the video game, but you want to train something for a robot, for instance, it's not going to have the textures of a real situation. But what you can do is use something like a style transfer, or what's referred to as domain adaptation, and add those styles, add those textures to the synthetic data, so that you can use it to train your model, and it will still generalize well enough to the real-world application. So there's a lot of really cool things going on with kind of these generative models, and as I mentioned, we're really only going to cover the very basic starting point from which these grow. But the GAN is, in particular, one of the models which has blossomed into a real abundance of different models. So I guess I'll leave off just showing the page maybe that I mentioned earlier here. Let's see if that pulls up. So here's the list of the implementations. So there's all of these GANs. And I highly recommend looking at this. You can see all of the different loss functions that they use and see how they implemented that. It's a great reference for moving forward and kind of going beyond the scope of what we've covered here. But this is the basic background that you need to kind of dive into this. And so yeah, I think I'll leave off here, and then we can come back at 4 o'clock, and we'll go over the next model that I wanted to go over, which is the Variational Autoencoder. Okay, so just take a quick 10-minute break. Thanks.